Okay, so going through the questions here, I'm going to share my thought process how to solve them. So this first one here says, all the reactions represented above occur in an aqueous solution of oxalic acid. Which of the following represents a Bronsted-Lowry conjugate acid base pair? So what I would do in solving this is whenever you're looking for a conjugate base pair, it's just the difference of something that has an H and then to something that lost the H. So I wouldn't even look at the equations. I would just look at the answer options and see the difference here. So A isn't right because it has 2 H's and now 0 H's. And the pair will only have lost 1 H. The next one has 1 H. And then the other thing is as it loses its H, its charge should change by a negative. And so this one, B, looks right, is the right answer because it has HC2O4 minus. And then the conjugate that remains just has the same thing with a 2 minus and missing the H. So the problem with C is C doesn't even pair up 2 of the right things. And then D has a difference of 2 H's because this has 3 H's on it and this only has 1. So there's number 1. All right, number 2 says, the table above shows the values of Ka for 4 weak acids. Which of the following pairs of chemical species, when combined in equal molar amounts, results in a buffer of a pH closest to 7.5? So the key part to remember in here is the pH of a buffer is equal to the pKa plus the log of A minus over HA. This is on your formula sheet, by the way. But if these two things are equal, the log of 1, because if they're equal to equal 1, is 0. And so we're really looking for that the pH of the buffer is going to be equal to the pKa of the acid. And so in looking at our acids here, we're given Ka values. So to get to pKa values, you take the negative log of the Ka's. So you could plug each of these values in for the negative log and find the value, or the shortcut way to estimate a log number is to just look at the exponent. So this one would be close to 4, this one would be close to 5, this one would be close to 8, and this would be 10. And so the one that when plugged in is the HClO buffer, and so the answer is C. All right, question number 3. So the following all relate to this. So we have a 50 milliliter sample of this unknown acid. The pH of the resulting solution is measured as we titrate with a 0.1 molar base that's added. Question number 3 says, at point R in the titration, which of the following species has the highest concentration? So at point R, okay, so remember in a titration, at point Q, right, we only have HA. Right, so at point Q, we just have HA. Then as the titration progresses, you're dropping in the strong base. It's reacting with this, so this reacts away and makes A minus. So every time, I'm going to change colors here to see. So every time this reacts, so this shows it reacts, it would make that much more A minus. Now the equivalence point is the point at which this is all gone. Okay, so that would be this point right here on the graph. So the point at which, kind of a helpful point, is the halfway point. So since equivalence was at 40, the halfway point of 20 is where these two would be exactly equal to each other. So since point R is right before that halfway point, that means we still have more HA than we have A minus. We're not going to have as much of this because it's a weak acid, and weak acids don't break apart much. And then the base reacts away when you're before the equivalence point. I don't know, right? Away. Question 4 says, which of the following is the best particulate representation of the species, other than water, that is present in significant concentrations at point U? So similar question, but now we're just picking the picture. So point U up here on our graph, right, is after the equivalence point. So one key thing is at that point, there should be no HA present. So that narrows it. That can't be C or D because those still show HA floating around, and after the equivalence point, all the HA has reacted. And then the next biggest thing is that at U, we are past the equivalence point, so you should have excess base that didn't react with anything. A would be an example of like at the equivalence point, because you don't have excess OH and all the HA has reacted, and so you just have the products that have been made. Number 5 says, at which point the titration curve is A minus to closest to that of HA. So once again, these are all connected to each other in understanding these questions. Once again, as we address that S, right, S is the point at which they're equal. And so if at this point I want more A minus, that means I want going past S. But if I still want HA to be here, we can't go past the equivalence point, and so that's why it would be point T. All right, and then number 6, a student carries out the same titration but uses an indicator instead of a pH meter if the indicator changes slightly past the equivalence point, which means I added too much base because it was supposed to be equal, but I went too far. What will the student obtain from the calculated concentration of the acid? So I'd first start with just finding it if it wasn't a mistake. So the equation for the equivalence point is the M of A, V of A equals M of B, V of B equation. And so the M of A is the molarity of the acid we're trying to find. The volume of the acid is the 50 milliliters that they told us we started with, so the volume of acid. The molarity of the base is also given in the problem here. So we have a 0.1 molarity of base, and then the volume of the base is how much we put in to get to the equivalence point. Okay, so if I rearrange that and solve for M of A, right, we'd have 0.1 times 40 over 50 to get it by itself, and that equals, when you plug that in, 0.08. And so that's what the molarity, this is what the molarity is if you didn't make a mistake. And so since we added, right, too much base, then we would estimate too high of a concentration. Because theoretically, like right here, instead of 40, maybe it would have been like 42, right? Which the top of the fraction here is bigger, then the whole thing would be bigger in the end. Okay, number 7. The table provides information on 2 weak acids. Which of the following explains the difference in their acid strength? So the strength of an acid is indicated by Ka value, because Ka value tells you the relationship of products to reactants. And so the higher this value is, the stronger the acid, because the more it's breaking down, and so the more product you have. So if I look at these numbers, let's see, so since this one is bigger, right, this one tells me that this is a stronger acid than that one. So that's a key thing I'm first going to start looking for, is I want acid 2 to be stronger. So that narrows out A and B. Now I just have to pick the correct reasoning. C talks about more polarizable molecules with stronger intermolecular forces than acid 1. D says because it has a more stable conjugate base than acid 1, which is the correct answer, because the key thing about what makes a strong acid is a stable base. Because remember, strong acids want to break apart, and so the thing they're breaking apart into should be stable. If it wasn't stable, then it wouldn't break apart. All right. So, to prepare a buffer solution for an experiment, a student measured out 43.49 grams of this salt. with a molar mass of this. So it's kind of important to recognize, like, oh, they're the same number, which means I have 1 mole of salt here. Okay. And then we added 1 liter of a 1 molar of NH3, which is a base. And so I have 1 mole of base. So we're adding, to make our buffer, we have a 1-to-1 ratio. However, in the process of adding the salt to the NH3, the student spilled some of the salt on the bench top. So we have less, right? So some of the bench top, as a result, only about 50 were added to the base. Which of the following best describes how the buffer capacity of a solution is affected by the result of the spill? So whenever I'm doing a buffer question, it's always helpful to identify, right, the 2 main components, which are, in a sense, HA and A minus, or, right, once again, acid and conjugate base, or the base and the conjugate acid, which would be HB plus. So in this case, this problem, right, we're in this situation of a base with a conjugate acid. And so the base is my NH3, right? So this is my base, and you can see the conjugate, so it's NH3, and so NH4 plus is the conjugate acid of that base, right, which is coming from the salt breaking down in the water. So it told us instead of 1-to-1, we have less of this than we meant to have had. And so then in terms of buffering, buffers buffer by opposites. And so the conjugate acid, right, the conjugate acid is designed to buffer the base. And the base is designed to buffer any acid. So since we have less of this one, right, that means it's not going to be as good at buffering base. So we're looking for an answer that's about better buffering the acid. So that narrows it down to C or D, because they both talk about that's going to be a greater buffering capacity for an acid. And the reason is because we have more base than we do acid in our buffer. And so any new acid that gets added is going to be better buffered away. Yes, buffers have a lot that go on to thinking about them. Okay, number 9. The acid dissociation constant for 2 acids are listed in the table above. A 20 milliliter sample of a 0.1 molar solution of each acid is titrated to the equivalence point with 20 mils of a 0.1 sodium hydroxide solution. Which of the following is a true statement about the pHs of the solutions at the equivalence point? So with an equivalence point, the value of the pH varies depending on the conjugate base that gets made. And so there's a pattern that the weaker an acid is, so this is like in any situation, the stronger its conjugate base. So it's kind of similar to that one we looked at earlier about the stability of the base. Stronger and stability go hand in hand. Okay, so if we're looking for, so number, or A says solution 1 has a higher equivalence point at the equivalence point because that acid is the stronger acid. So first thing, given the Ka values here, since this one is bigger, right, than the other one, we know that this one is stronger acid. So that one is not even a plausible answer because it's not true, right, that is not the stronger acid. Okay. It says here that solution 1 has the higher pH at the equivalence point because CH3COO2H has the stronger conjugate base. And so, based off our trend up here that we identified, right, the weaker the acid, the stronger the conjugate base, we know that this one is going to have the stronger conjugate base. So with this one, it is true in that it's going to have a stronger conjugate base. And so if the base is stronger, bases make pHs go higher. And so the answer is B. The reason why C is false is C says it's going to have a lower pH. Once again, the claim here, that one's not the stronger acid. Okay. And then this one here says that this one has a stronger conjugate base, which is also false. And so there you go. All right, number 10. So we have a weak acid with a pKa of 4.76. A solution is prepared by mixing that concentration and molarity of our acid with 0.2 moles of our NaOH. Which of the following can be used to calculate the pH of the solution? So in this question, you need to be able to recognize that they're making a buffer solution. There's a few ways, once again, you can recognize that is that you have a weak acid and a strong base, and that's a recipe for a buffer. This equation that they're plugging it into is also the equation only used for buffers. So that's a little bit of context clues. All right, that anytime we use this equation, it's only for buffers. So with a buffer solution, the basic idea, right, is we have our weak acid. So this is this guy. Okay, we're reacting it with our strong base. I don't care about the sodium side of it. Okay, they're going to make a minus and water. So the two components we need to find to plug into our chart here is we need to know how much HA there is and then how much A minus there is. Okay. All right, so we have to do a rice chart to see how much we start with and how much gets made. So the problem tells me here that we have that many moles of base, so that's easy, 0.02. For the acid side, they give us the volume and the molarity, but it has to be in moles to use the rice chart here. So we got to do a little side step of 0.5 liters times 0.15 mole per liter. Right, so that ends up giving us 0.075. Right, so that came from here. Okay, now for reacting, the base always gets used up because there's less of it. And now keep in mind the change should be consistent with the balanced equation. This is going to be 0, by the way, because it wasn't made yet. So we're going to have 0.02 moles of that, 0 of that, and then 0.055. And so then if you match that to what we highlighted before, right, this one goes on the bottom, this one goes on top, right, so here to here, here to here, and so that gives us the correct answer of, which one is it? C. Okay, another question about buffers, number 11. So this one actually, once again, it's helpful to recognize similarities among questions because then even as they change, you can kind of get the overall thing of what will be asked of you. So notice that this one actually has a similar idea to number 8 in that I always identify first when it's a buffer-like question. So this tells us we have an acetate buffer made by combining acetic acid, right? So this is going to be my HA. Get rid of this here for now. Okay, and then we're combining it with a salt. All right, so here's my salt. And so that substance right there, the C2H3O2 minus, is the A minus. So see the connection there between HA and A minus. Okay, it then tells us that we're adding a strong base to the buffer system. Yeah! Okay, so with our strong base being added to the buffer solution, It says, then, which of the following, right, so which of the following is the correct pairing of the acetate species present in the greater concentration after the base has been added? And then it tells us the pKa of the acid is 4.7. Okay, sorry for the pause there. So the first thing I think about here, there's two parts obviously, is we need to pick the direction that the pH is going to go, and then which species, right, is in greater concentration. So the species present in the greater concentration, as well as the direction of the pH. So focusing on the pH change first, since I'm adding a strong base, I know that the pH is going to go up because bases make pH higher. So that's going to narrow down my choices to either B or C, because those both show the pH going up. Okay, and then the one in the greater concentration is going to take into account which didn't react, because then it didn't get used up. So keep in mind with a buffer, right? You think of it like a bar graph, okay? So you have this much HA and this much A minus in the buffer, okay? When you add, keep in mind these are like the same system, okay? When you add your strong base, so when the strong base is added, remember, opposites react, and so a base, right? So a base is going to react with an acid. So this amount is going to go down, right? Just showing that's getting used up as it reacts with the strong base being added. So the one that's going to be present in a greater amount is the A minus, because it wasn't used with the addition of the base. And so that's why the answer is D. Okay, number 12. Which of the following accounts for the observation that the pH of pure water at 37 degrees Celsius is 6.8. So with this question, right, it's keeping in mind how equilibrium shift with temperature changes, and so pure water being at 7 is for when it's at the standard 25 degrees Celsius. And so A is incorrect because no, water is not naturally acidic. B says that at 37 degrees, the autoionization constant for water, Kw, is larger than it is that at 25. So Kw is on your formula sheet, but it's a relationship of H plus and OH minus. It normally equals 1 times 10 to the negative 14, which is where, once again, we get that, the pH scales from 0 to 14. And the key thing, too, is that these two things are always equal in water, no matter even if it shifts. So if it's getting more acidic, as this would be showing, then that corresponds to K. I guess the thing you want to look for is, if K gets bigger and I cut it in half, would it be 6.8, or if its K is getting smaller? And also, in a sense, taking the negative log of it. And so in it, that is why it does end up being B. The other answers are, once again, this one says that H plus is greater due to density, which really doesn't make sense. And then water ionization is to a lesser extent than it does at 25 degrees. But if it was lesser, then you would have less H plus. So there's that one. Okay, number 13 talks about buffer capacity. And it wants to know, of the different solutions, which one is going to have the greatest buffering capacity. So buffering capacity would show just which one has the most of both the acid and its conjugate. And so that's why the answer ends up being D, because you have the highest molarities of both. All right, so you want similar numbers, but you also want the highest number you can. So technically, like if D was like really high on this side, but like 0.1 on that side, I probably wouldn't pick it as my option. I think probably more like C would be a better option because they're fairly equal and the highest. All right, 14 says, samples of these two are dissolved in separate beakers that each contain 100 mils of water. One of the salts produces a slightly acidic solution. Which of the following equations best represents that formation of a slightly acidic solution? So the first thing I would look for is if I'm looking for an acidic solution, then that means I need some free floating H+, which is the same thing as our H3O+. So right away from that, I can narrow it down that it must be either A or C, because those are the ones that have a slightly acidic solution. Then what you want to look for next is the other thing that gets created. Since this is a strong base, then the reaction would be pushed back the other way, which means this really isn't made. But since this one is a weak base and stays together, then this is the one I'd pick, and it is C. All right, last three. Okay, so we have this big data table of these different types of acids, their molar masses. Their only difference here is this X. It's either F, Cl, Br, or I. Okay, 15 is review from Unit 3 about IMFs. It says which compound, the chloroacetic or iodoacetic, most likely has a lower boiling point, and why. So first thing I would think about is what type of IMFs do both these have, and looking at the structure, they both have hydrogen bonding because of this. They both also would have dipole forces because it's a non-symmetrical structure. Right, if I look at the structure, it's not symmetrical. And what will increase dipole over one or the other is electronegativity. So the higher, not the pencil. The higher the electronegativity of this one, since that's the only difference, the more dipole it's going to have. And so since I'm comparing chlorine to iodine, this one is going to have more dipole forces. Okay, and then our last type of forces, they both have London, but the one that's going to have more is the heavier it is, the more London, so this would have more London. Okay, so I've kind of identified what forces. It can't be because of hydrogen bonding because that's the same, but it could be because of those. The other thing to keep in mind is if something has a lower boiling point, then that must mean it has weaker forces. So we need to make sure our answer option supports that. So the first one says that it is the chloroacetic acid because the London dispersion forces of this molecule are weaker. So that is logical in what it's saying, that it would have a lower boiling point because its forces are weaker, which is the right answer. But let's go through the other ones and see why they're wrong. B, chloroacetic acid because the dipole forces are weaker. But as we identified up here, right, that the chloroacetic has more dipole, and so that is a false statement in claiming that the dipole forces are weaker. The next one says ioacetic acid because the London dispersion forces in that molecule are stronger, which this one is a true statement, right? We do know its London are stronger, but that would not support the fact that we're looking for the lower boiling point. So it would not be lower because its forces are stronger. And then the last one, false claim, where it says the dipole forces are stronger, which is also false. All right, 16 says an aqueous solution contains small but equal concentrations of chloroacetic and fluoroacetic acid. Which statement comparing percent ionization of the two acids is true? So percent ionization is really another way in which you can state the strength of an acid or how much it breaks apart, I should say, because the higher the percent ionization, the stronger the acid. So in a sense, in a fancy way, this one is asking you to compare the strengths of the two acids, because once again, the higher the percentage, the stronger the acid. So if I look up here at my chart, Ka is also a measure of the strength of an acid, where the bigger the K, the stronger the acid. stronger the acid. And so I'm comparing, let's get rid of some of this from the other one. Okay, so I'm comparing this guy, what am I comparing? And
hi, this is Blake
this
Erickson,
one.
next year's student body president. If you're a current junior or sophomore, please get on the Canvas course and vote for next year's class officers. Voting closes today at 2:45. Thank you.
Pardon the interruption. Okay, so for this one, since this is a bigger number, this tells me it's the stronger acid compared to that one. So I need to pick the answer that talks about fluoroacetic having a higher percent ionization.
Hey.
Hello.
Yeah, I was just wondering the straw.
All right, last one, 17. A student titrates 10 mils of a 1 molar sample of each of the acids with a standard solution of NaOH. Okay, so key thing with titration is recognizing we're using the same concentration of base for each. Which of the following statements correctly predicts the volume of NaOH needed to reach the equivalence point? So equivalence point is the point at which the moles of the base equal the moles of the acid. And so since you're using the same concentrations for all of them, they will take the same volume to get there. If it helps you to see it mathematically, our equation for equivalence point is this, M of B, V of B. And so since it's the same M of A, M of, this should be the V, and this one would be M of A. So for all the acids, those are the same. And then the concentration of base, this would be the same. All right, so if these are the same, this is the same, then every time the volume of base will be the same. Hope that helps. Come see me if you have any more questions.